Hello! Just a heads up before we begin, this video is not meant to be an introduction to the chain rule. I will assume that you've already done some practice problems taking the derivative of various expressions using the chain rule. This video is intended to build off of your understanding of the chain rule. In particular, I'd like to explore further the idea that a derivative is an uncertainty multiplication factor. It tells us how much an uncertainty in the input gets multiplied by in giving us an uncertainty in the output. And in particular, what that means in the case where we're applying multiple functions to a particular value. That is a composition of functions, so we're interested in the chain rule. So hopefully this video will help build on your understanding of the chain rule and its physical significance, but this isn't meant to introduce you to the chain rule. I'll start off with a single value x as 3 plus or minus 0.01, and in particular that means that x is in the interval from 2.99 to 3.01. As I mentioned in the previous video, this plus or minus notation, meaning that a value is strictly within a range, is actually very rarely used, because it's very hard to establish that a particular value is strictly within a particular range in the real world. There's always a level of uncertainty to your uncertainty. But for now, for this video, you should view this as x being strictly within this range, and actually it doesn't fall apart too much if you think about this as x probably being in this range. And suppose that we're interested in calculating g of x, where g is the squaring function. So the first thing that we do is we take our base point, right? X is approximately equal to 3, and we plug it into our function. We square it. So, and this will be our base point, and then we have to calculate our level of uncertainty. And the way that we can do that, as I showed in the previous video, is by multiplying our uncertainty from up here by the derivative of our function at our base point, at 3. So we need to calculate g prime of 3. G prime of x is equal to 2x, and then g prime of 3, which is 6. So we need to multiply 0.01 by this derivative by 6 to get that g of x is going to be 9 plus or minus 0.06. Now, this isn't our exact g of x, it's only an approximation, but it's a really good approximation because we started off with a very small level of uncertainty. In particular, this here says that g of x should be between 8.94 and 9.06, and actually, if we're looking at this particular range, and we take all these values and we square them, that's actually going to be 8.9401 to 9.0601. So this here, this is actually just an estimate, and we're actually off by, and it's only 1/10,000th, so that's fine. But that's what I mean when I say that the derivative is the uncertainty multiplication factor. It's the thing that we need to multiply our initial uncertainty by in order to get our new level of uncertainty of the output of a function. And as our uncertainty level gets better and better, as this number gets smaller and smaller, this approximation gets better and better. So now suppose that we're interested in applying a function to this value here. Suppose that we're interested in applying f of x equals x minus 8 to the 5th to this value here. Well, again, what we need to do is we need to take our base point and we need to apply our function to it, and that's going to give us the base point of the result. So we plug 9 into f of x, and it's 1 to the 5th. And then this uncertainty factor gets multiplied by the derivative of this function here at the point at our base point. So in particular, the derivative of f of x is going to be 5 times x minus 8 to the 4th times the derivative, right? So this here is a chain rule problem, right? You take the derivative of the outside function is x to the 5th, So it's going to be 5x to the fourth. We leave the inside function, x minus 8, alone. Then we multiply by the derivative of the inside. And luckily, in this case, the derivative of x minus 8 is just 1. So this whole thing is just multiplying by 1, so we don't need it. So here's our derivative, f prime of x. We need to evaluate this at 9, at our base point. And again, we're going to get 9 minus 8, which is 1. So 5 times 1 to the fourth, which is just 5. So that's going to be our uncertainty multiplication factor here. We take this uncertainty here and we multiply it by 5. So it's going to be 1 plus or minus 0.3. And the value that we got here, we got by applying our f function to our, well, it's only an approximation, but it's to our approximation of g of x. So we took f, we applied it to g of x, we approximately got 1 plus or minus 0.3. So that is, we suspect that this value falls roughly in the range between 0.7 and 1.3. And again, this isn't exact, this is just a really good approximation. It's a little bit less good because we're starting off with a bigger uncertainty, but it's still pretty good. It's still a pretty good approximation, and it's sometimes very useful to be able to very quickly come up with these approximations, as opposed to having to sit down and actually plug these endpoints into these functions here. So it might help to plot out what we've done here. We started off with 3 plus or minus 0.01, and then we wanted to apply the g function to this. So we applied g to our 3 to get 9. Again, g was our squaring function. And then in order to deal with the uncertainty, we multiplied by 6, by g prime of 3. And that looked like this. And then we wanted to take our 9.06, we wanted to take this result, this g of x, and we wanted to apply our function f to it. We applied our f to 9 to get 1, and then we had to multiply our uncertainty by the derivative of f at 9. That was times 5 to get 0.3. So our final value was approximately 1 plus or minus 0.3. And that looked like this. And when we put these two functions together, right, when we're interested in taking f of g of this value here, we're simply composing these two functions. This first function here, multiplying the uncertainty by 6, and this second function, our f, multiplying the uncertainty by 5, because that's the slope here. And so the result, the composition of these functions, again, this is, we're applying f to g applied to our original x value. So this is going to be f of g. It's a little bit confusing, the order that things go, right? They go from right to left, and it's a little bit backwards from what we're used to. But we call this composition here f of g because we're taking f of g of x. And this composition here multiplies the uncertainty approximately by the product of these two values. So we're multiplying our uncertainty by 30, going from 1/100th to 3/10. Now it's worth spelling out exactly what these values are. This value here is our g prime of 3. This value here, this 5, was our f prime of 9, which in particular, that 9 came from taking g of 3. So that's f prime of g of 3. And the product of these two values gives us the derivative of f of g of x at 3, right? If we view this as a single step, the value that we're plugging in, our base point is 3. So this here, this uncertainty multiplication factor, should be the derivative of this function at this base point. So in particular, the derivative of f of g, the derivative of the composition of these two functions, evaluated at 3, is going to be equal to the product of our g prime of 3 times our f prime of g of 3. And this works for any value of 3. In particular, the derivative of f of g evaluated at any value x is going to be g prime of x times f prime of g of x. So this here is our chain rule. It's probably backwards from what you've seen. You've probably seen the f prime of g of x going first, but that's fine. The order of multiplication doesn't matter. But the key idea is that the uncertainty multiplication factor for a composition of two functions is just the uncertainty multiplication factor of the first function times the uncertainty multiplication factor of the second function. But the tricky thing is that when we evaluate the second function, we're doing so at not our original x, but g of x. Now I want to show you how we can solve a very general chain rule problem using this uncertainty multiplication factor perspective of the derivative. So suppose that we're interested in, we have some sort of composition f of g of h of x, and we're interested in taking its derivative with respect to x. Looking at this from an uncertainty multiplication factor perspective, we start off with x, and that has some level of uncertainty to it. And then we apply our function. Now the first function that gets applied to x, remember your order of operations, you're working from inside out. So first we apply h to x, and that'll give us h of x. So first we apply h, that gives us h of x. And so we're going to multiply this uncertainty here. We don't know what that uncertainty is, but that's fine. We also don't know what x is. We multiply this uncertainty here by h prime of x, the derivative of h evaluated at our base point here, x. That's going to give us our new uncertainty. Now h of x, we want to apply the function g to that. And to get from this level of uncertainty to this level of uncertainty here, we're going to want to multiply by the derivative of g. But we want to multiply by the derivative of g at our base point for this step, at the actual base point of the value that we're plugging into our function g. And so we want to multiply by g prime, not g prime of x, because we're not plugging x into g, we're plugging h of x into g. So it's g prime of h of x. And then finally, we have our g of h of x. We want to apply f to that. We want to take f of g of h of x, and that's going to have some level of uncertainty to it. And so we want to multiply this uncertainty here by f prime, and again it's going to be f prime not at x, not at h of x, but f prime at the actual value that we're plugging, at the actual base point that we're plugging into f prime of g of h of x. And so overall, right, our triple composition f of g of h takes us from x down to here. Let's write that as f of g of h. And then the amount that this uncertainty got multiplied by is going to be, well, it's going to be, we first multiplied it by h prime of x, and then we multiplied it by g prime of h of x, and then finally we multiplied it by f prime of g of h of x. And so the total amount that we multiplied by is just the product of these. So the uncertainty multiplication factor associated with f of g of h is just going to be h prime of x times g prime of h of x times f prime of g of h of x. Right, we were able to figure out the derivative of this composition here by thinking of it as an uncertainty multiplication factor when we apply the triple composition function here. And this agrees with what we get when we do the symbolic derivative. Right, when you're doing a chain rule problem, you're probably not thinking about uncertainty multiplication factors. You're probably thinking about, right, take the derivative of the outside, leave the inside alone, then multiply by the derivative of the inside. Let's do that for this here. I realize this looks like an intimidating problem, but if we just follow the derivative rules, we'll be perfectly fine. We do the same thing that we would for any other derivative problem. We start off by asking, what's the outermost operation here? The outermost operation in this case is applying f to something. We don't care what just yet. So it's going to be a function application. And so that tells us that we want to use the chain rule. So we take the derivative of the outside. Now you're probably thinking, hold on, we don't know what f is. We don't know what the derivative of f is. But that's perfectly fine. The derivative of f, we just write it as f prime. So this is going to be f prime. We take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. Now, if you're impatient, you're probably going to want to take the derivative of the inside right away. That's going to be another chain rule problem. But I really like solving a derivative problem, especially a chain rule problem, in steps. So I'm just going to write here that I need to figure out the derivative of the inside. And I'll come back to figuring that out later. Now, this is really handy. I realize it's an extra step, it's an extra thing that you have to write, but this is really handy when you come back and check your work and have to remember what it was that you were doing as you worked through this problem. Here you can remember that, yes, I took the derivative of the outside, left the inside alone, multiplied by the derivative of the inside, and then went on to figure out what this derivative was. I did that in multiple steps. So this sort of practice here of leaving some parts of your formula unevaluated, we still need to take the derivative here, I think is a really good practice for making it easier to check your work. So now let's do that. Let's take this derivative here. This derivative here, right, how do we evaluate a derivative? Well, we ask what's the outermost operation. The outermost operation in this case, we're applying the function g to something. We don't care about what that is quite yet. And so we use the chain rule. It's the derivative of the outside. Again, we write that as g prime because we don't know what g is. Leave the inside alone and multiply by the derivative of the inside. And this agrees. Again, the order of multiplication doesn't really matter. So this here agrees with the derivative that we calculated this other way. So note what's going on here. Every time we apply a function, we're multiplying by a derivative of that function, evaluated at some point, in particular the point that we're actually evaluating the function at. But we're multiplying the uncertainty by a derivative of our function. And so what that means is that depending on what sort of derivative we're looking at, if we're applying lots of functions, we can have a very large uncertainty multiplication factor or a very small uncertainty multiplication factor. Right? If all of these derivatives were 0.1, we take our original uncertainty, we multiply it by 1/10 and multiply it by 1/10 again, and multiply it by 1/10 again, we would get 1/1000th times our original uncertainty. Our uncertainty would improve by 3 orders of magnitude. On the other hand, if our derivatives were larger than 1, let's say they're all equal to 10, well, we're taking our original uncertainty, we're multiplying it by 10, multiplying it by 10 again, multiplying it by 10 again, then we've taken our original uncertainty and multiplied it by 1,000. And so if we started off with an uncertainty of like, I don't know, 0.01, we'd have an uncertainty in the end of 10, right? It'd be plus or minus 10. So depending on whether these derivatives are larger than 1 or smaller than 1 in magnitude, that's going to drastically affect what happens to our uncertainty, whether it gets larger and larger, whether we're multiplying it by things that make it larger and larger, or whether we're multiplying it by things that make it smaller and smaller and smaller. If we have lots of functions, well, that can get it can get very large, exponentially large or exponentially small. Let's do an example where this happens. Let's consider this function here. its graph looks like this, and notably the slope of this graph, the derivative of this graph, is pretty much 2 everywhere, except at the points of discontinuity of the graph. And that's going to make our reasoning about the chain rule for this function much easier, because if we're talking about the derivative, it's pretty much always going to be 2, regardless of what value we're plugging in. If we took this function and composed it with itself 4 times, and tried to take the derivative, well, again, we can figure this out using a chain rule, or by using kind of a uncertainty multiplication factor approach. Either way, you're going to wind up getting something that looks like this, right? The derivative of the innermost function at the point that we're plugging into that function times the derivative of the second innermost function at the point that we're plugging into that function times the derivative of the third function at the point that we're plugging into that function times the derivative of the outermost function at the point that we're plugging into that function there. And again, the nice thing about this function is that we don't need to worry about what f of x actually is. If we're taking the derivative of f, it's pretty much always going to be 2. So unless we got really unlucky and one of these values gives us one of our points of discontinuity, the value of this product here is going to be 2 times 2 times 2 times 2, 2 to the 4th, or 16. And we can see that when we actually go to plot out f composed with itself 4 times. This graph here, the slope is almost always 16, except at a few points of discontinuity, which are caused by plugging in some value that gives us, 1/2 or 0 or 1 into one of these functions here. And as we can also see, the slope of the function is already getting a little bit out of hand. It's very difficult to control the output of this composition by controlling the input. And you could imagine if we composed f with itself even more times, the resulting function would have an even steeper slope and would be even harder to control the output by controlling the input. Because every time we compose with a new f, we're multiplying by a new derivative of f, we're multiplying by 2, the slope, the derivative of this thing, is going to be 2 to the power of the number of times that we compose the function with itself. And 2 to the power of n grows really quickly. If we composed our function with itself just 20 times, the resulting slope would be just a little bit over 1,000,000. And again, the slope is the uncertainty multiplication factor. So in order to control the output of this function, we would need a massive amount of control over the input of this function. And if we wanted to predict the output of the function, we would need to know the input to the function with an incredible amount of precision. So even though these compositions have really straightforward graphs and it's really easy to calculate the actual value of these functions at any one particular point, we call these sort of processes where we iterate these sorts of functions, where we apply these functions over and over and over again, chaotic. Because even though the function is straightforward and mathematically predictable, when we encounter these sorts of functions in the real world, because there's always going to be a certain amount of uncertainty about an input to the function, about the state that we start out in before we apply the function over and over and over again, that uncertainty is going to magnify. It's going to be multiplied by 2 to the power of n, where n is the number of times we're applying the function, and eventually it's going to get out of hand, no matter how good our original precision was. So we describe these sorts of situations as chaotic. Now, I'm kind of oversimplifying the situation here a little bit. In order to have chaos, it's not enough to just have a slope that's larger than 1 pretty much everywhere. If we consider, for instance, the function f of x equals 2x and applied that function to itself lots of times, we get exactly the same sort of situation where the slope of that function was 2 to the power of the number of times we applied the function to itself. Yet nonetheless, repeatedly applying the function f of x equals 2x is not considered to be a chaotic system. because controlling how far the input is between 0 and 1 gives us control over the fraction of the way that the output is between 0 and 2 to the power of however many times we've iterated the function. So the only thing that really happens in this case is that we get large outputs. We don't get uncontrollable outputs. Somehow the fact that this function is folded in on itself, that the outputs for these inputs and the outputs for these inputs are the same, contributes to this being considered chaotic, and repeated application of the doubling function to not be considered chaotic. So there's a little bit more going on. I'll link to some resources if you want to read more in the description below, but that's not really within the scope of this video. Now, chaotic systems are very difficult to predict and control. Small changes, sometimes changes smaller than your ability to perceive to the initial state of the system, can get magnified over and over and over again to create massive changes to the resulting state of the system. And usually that's very unpleasant, but sometimes we want that. We want a level of unpredictability to our systems. For instance, when we're shuffling a deck of cards, we want it to be the case that the initial position of the card within the deck tells us nothing about the final position of the card within the deck. We want complete uncertainty. And to get that, we can take advantage of a chaotic system. If I take a deck of cards, cut it perfectly in half, and perfectly interleave the two halves of the deck, the function that tells us the position of a card after this interleaving, as a function of the position before the interleaving, looks something like this. Look familiar? This is almost exactly our example from earlier on in the video. And so every time we cut our deck in half and interleave the two halves, roughly speaking, we multiply the distance between two cards, or the uncertainty we have about the position of an individual card, roughly by 2. Of course, when we shuffle a deck of cards, we aren't doing a perfect cut it in half and a perfect interleave. There's a little bit of randomness. And so if we shuffle the deck multiple times, that little bit of randomness is going to be magnified over and over again by the interleaving process. The first shuffle introduces a little bit of randomness, and then the next shuffle magnifies that little bit of randomness and introduces a new bit of randomness. And then the next shuffle takes those two previous bits of randomness and magnifies those and introduces its own bit of randomness. When we reach approximately 7 shuffles, the amount of randomness, the amount of uncertainty that we introduce, has been magnified to be larger than the size of the deck itself. That is, we have no idea where any of our cards wind up in the resulting deck. And so if you've heard the recommendation that you shuffle a deck of cards at least 7 times to get it random, this is one of the places that recommendation comes from. There are other more advanced mathematical models for shuffling a deck of cards, and those also predict roughly 7 shuffles will get the deck random. I'll link to some information about those more advanced models in the description below. So I hope this video has helped give you some perspective on the chain rule. Understanding the derivative as an uncertainty multiplication factor helps make the chain rule more intuitive, and can help us better understand some real-world phenomena where a function gets applied over and over and over again to the state of a system. So, thanks for watching. Please leave any questions or comments you might have down below, and be kind to each other.